Brian, good morning, good afternoon, or good evening, depends on where you are in the world today. What we have this morning, which is what we have today from our Water Loss Specialist Group webinar series, is a presentation from Heiko, which is based down on the Gold Coast in Australia. And he'll be talking today and talking us through how to reduce losses on pipelines using some sort of rehabilitation technology and techniques. So I think enough said by myself. Over to you, Heiko, and thank you very much indeed.
Thank you very much. Thank you for the introduction, and welcome everybody. Thank you to the IWA, of course, for giving me the opportunity to present today. Our topic today is non-revenue water reduction using trenchless technology. So that means I'll give a short introduction into NRW, and then we have a look at what technologies are out in the market to reduce water loss in pipelines. And then we want to have a quite more specific look at one certain technology, which is the rehabilitation of pipelines with inserted hoses. Then let's first have a look in general at non-revenue water. So what is non-revenue water? How is it defined? So basically it's the water we produce minus the water we lose on the way before it reaches the customers. And if we look at the numbers are actually very, very impressive. That's the latest number, the numbers I found, even if they are now 2-3 years old. So we have about 126 billion of cubic meters of water that get lost on the way. And the cost here are roughly 39 billion American dollars. The loss, of course, is different in different countries. Yeah, so you can't say that in every country you have the same numbers. I remember from some time ago when I was working in South America, that in Brazil, sometimes in some occasions when I was speaking to water utilities in Rio de Janeiro, for example, they have up to 90% of losses, depending on where the pipeline sits. So that's, of course, tremendous. Yeah. But then how is that water loss in general defined? Well, as you can see here, it's first of all the not counted authorized consumption. Then the next part is commercial losses like thefts, handling errors. There are sometimes people just come drill a hole in your pipe and they steal your water before it reaches the end client. And the main loss that we have in our pipeline systems at the moment are physical losses. So that means we have leaks in our pipelines. The pipelines are in poor condition, and the rest of the water then gets to the client. But let's now focus on the physical losses. So the physical losses are responsible for over 60% of the total loss that we have. And like I just said, of course, and what we see also here on the pictures, it always depends. Pipelines move, the grounds move, soil moves. So you get joint deflections in the pipelines where water can just sneak through the joints. Over time, pipelines crack. You get holes through corrosion, for example, or the pipelines are laid in contaminated soil. So you get corrosion from the outside and so on and so on. And here, to fix those issues, trenchless solutions are perfect. So we want to take a closer look today in technologies that are defined in the DIN ISO 11295. And if we have a look at the chart here, we see that we basically have three main columns. So first of all, what you can do if you find that you have a leak in your pipe, well, of course you can repair it. So repairing means you can you dig down and you, for example, put a clamp onto the pipeline, so you do a local repair. Then the next big thing is renovation. I'll come back to that in a second. And then the last column over on the right is replacement. And replacement can either be with traditional methods, so dig and replace. So we dig the old pipe out and we lay a new pipe, or we use trenchless replacement technologies like pipe bursting or horizontal directional drilling. But then let's focus a little bit more on the renovation today. So we see that under renovation, there are numerous technologies, and I would like to show you a few of them. And then, basically I want to focus a little bit more on the rehabilitation of water pipelines using inserted hoses, because this is also what we do, and this is what I know, right? So first of all, I would like to show you a technology, CIPP, cured in place pipeline. The CIPP technology comes actually from sewer pipe rehabilitation, and it is used in sewer pipe rehabilitation still all over the world. It is the leading technology, in my opinion, for sewer pipe rehabilitation. It has been around since, I think, about the late 80s or so, invented in the UK. And there are different methodologies also within the CIPP. This specific one here for the potable water application is a UV light cured CIPP. So what this technology is, so you have a hose, a felt liner. This liner is has resin in its felt. Then you clean the existing pipeline, you pull the liner into the existing pipe, you inflate this polyester or this felt liner, you bring it back you bring it in this round shape, and then to cure the resin, you pull a UV train through what we see here in the graphic on the screen. And when you pull this UV train through the liner, the resin hardens, and it gives you basically a new pipeline in your old pipeline. The next technology here is thermoformed pipes, or U-liner. U-liner, you get it why? It's the form of the pipeline. So it is basically a plastic pipe which is pre-formed into this U shape before the insertion into the existing main. And this is of course done because it reduces the friction. You can easily install that U-liner into the existing pipeline. And then once you have your thermoformed pipe inside your existing pipeline, you use steam or hot water. And plastic, as we know, has a memory function. So that means by heating up the material, your U-liner goes back into the round shape, in that shape that it was produced originally. The next technology here that I would like to share with you is slip lining. In my opinion, I think slip lining is the most common way to rehabilitate a water pipeline. It is also used basically all over the globe. What you do here is you take, again, PE pipes, plastic pipes, and you insert them into the existing pipe. It can be either one continuous long plastic pipe, what we see on the picture on the right, or you can also insert pieces and then weld the next HDPE shot onto the last one, and then you continue inserting and continue inserting. Also, this is a rehabilitation method for pressure pipes, for water pipelines. But let's come back to the graphic now, because now what we want to focus on, we have now touched a little bit on different technologies out in the market, but I would like to give you now a deeper insight on lining with inserted hoses. So lining with inserted hoses is a bit different to what we have seen up to now. This system, specifically now the premise line system, for example, always consists not only of that flexible pipe, that flexible liner, the hose, but also it needs end connectors to connect to the existing pipeline system. And only together they form this rehabilitation system. So you can not only install a liner like you can, for example, with CIPP. Well, they also have end caps, obviously, but the connection technology is different, or with slip lining, for example. With the premise line system, or in general, with lining with inserted hoses, you always need a specific end fitting. But let's first talk about the liner, and more specifically about a premise liner in this case. So you see that the liner has 3 layers, and it's also the little sample that I hold here in hands. We can also see the 3-layered structure. We have a outer layer in this case, which is a pure protective layer. When you insert the liner, the hose, into your existing pipeline, it is like a protective layer. And also later on during operation inside your existing main, this layer serves as a protective layer. Then the next layer is our internal layer. So that's the black one that we see here. And the black layer is the layer that carries the medium, in our case, the potable water. In general, this layer here can also be adapted to other mediums. So if we want to transport, for example, let's say aggressive sewage, or we want to transport diesel, we want to transport crude oil, all that is in general also possible with inserted hoses, but you have to adapt the inner coating to another type of plastic. In this case here, it's polyethylene, but we can also use, for example, a thermopolyurethane, a TPU. What's also a big benefit of the relining with inserted hoses is the low friction coefficient. So with every relining technology that you use, you of course lose a little bit of diameter of your existing pipeline because you put a new type of pipe in an old pipe. But the beauty of this inner coating here is the low friction coefficient of only 0.028. And that, of course, is fantastic when you do your flow calculations after the rehabilitation. It might even be that it depends, of course, what the existing pipeline was and what your existing flow coefficient was, your friction coefficient. But it might even be that you rehabilitate a pipeline with an inserted hose, and after the rehabilitation, you even have a better flow than before. And we had cases like that already. The next layer is our core layer. This is also what in this case makes this specific liner, the premise liner, worldwide unique. So the core of this liner is made from Kevlar. So Kevlar is an aramid fiber. It's basically the same material that is used on bulletproof vests one-on-one. And the big benefits of this Kevlar material, of this aramid fiber, are that it is an extremely strong material. So that means for a producer, for a user, and also for an end user that uses the liner in his own pipeline, is that you can operate this liner very thin wall, but still with very high operating pressures. What I mean by very high, I show you in a second. And you can also insert this liner over very long lengths. And we'll speak about also the installation process in a second. But when this liner is being inserted into the existing pipeline, it is similar to what we have seen before. The liner is being winched into the existing pipeline. So you pull, you drag it into the existing pipe. And that means that your materials, they have to bear the pulling forces, of course, during the insertion process. And the Kevlar here allows us to install such a liner over the length of 1 kilometer. even more than 1 kilometer. We already installed 3.6 kilometers in one single go. All that only possible while we use, because we use Kevlar fiber. The liners that are being produced at the moment are ranging from 150 to 500, but due to the fact that this liner here, this hose, is a self-supporting liner. So this means that the liner can actually hold the operating pressures in your main. So when you install this liner into your existing pressure pipe, into your water pipe, this liner will actually withstand the operating pressures. And your hose pipe is basically only a conduit that guides the liner from A to B. So that also means, despite we, for example, only have a DN500 liner available, you can easily also rehabilitate a DN600 pipeline with a DN500 liner. The liner just sits loose fit in the pipeline, no grouting necessary, if you, of course, can accommodate the loss in diameter. But I'll give you a few examples on that a bit later on in the presentation. Then let's speak about the product portfolio of the available liners. And what we see here at the moment is that every liner, every hose is rated to a different maximum allowable operating pressure. So I would assume that most of you out there are familiar with, for example, HDPE pipelines. And HDPE pipelines are always rated to a certain operating pressure, PN6, PN10, PN16, and so on. And the wall thickness of the HDPE pipe gets always a little bit larger, the larger we get in diameter, and the larger the operating pressure gets. So with Primus line, this is a bit different, because this liner here, this flexible hose, has a wall thickness of 6 millimeters. And it will always have a wall thickness of 6 millimeters, being a DN150, the one I hold here, or being a DN500 liner. So due to the fact that this liner does not get any thicker in wall thickness, you basically have to derate the liner in its maximum allowable operating pressure the larger you get in diameter. It's the same principle, just the other way around. This again just shows you that the standard liners, I'm not talking about our double layered liner, that's a different story, but the standard liners that are available for water installations always have a wall thickness of only 6 millimeters. So if you compare that, for example, to slip lining, what we have seen before, with slip lining, with the wall thickness of the HDPE pipe, as just discussed, you always lose a fair bit of diameter when you insert such a PE pipe into your existing pipeline. With a flexible liner, you always remain at a wall thickness of only 6 millimeters. Then let's speak about the installation process. So the flexible liners, the flexible high pressure pipe, however you want to call it, comes pre-folded on a transport reel. So again, similar to the U-liner that we have just seen, it's pre-folded in a U or C shape. Also here, this reduces the friction during the installation. And then by using a pulling winch, what we see on the right-hand side, the liner is being inserted into the existing pipe over long lengths. As I just mentioned, up to 1,000 meters are absolutely doable. Also over 1,000 meters are doable. And due to the flexibility of the hose, like here, you can also insert this hose through existing bends. So if you have, for example, a river crossing or a pipeline that goes under a road with 445-degree bends, by using a flexible hose, you can rehabilitate also such a pipeline. You could not do that with traditional rehabilitation methods. That would just not be possible. Then let's have a look at some videos. I hope the videos work all right for everybody. So on the left-hand side, we see the installation of a DN500 liner, about 500 meters directly from the truck through an existing maintenance chamber, so you can always keep the pits small as well, the access to the pipe. Then on the right-hand side, we see a 45-degree bend, open cut, but only just open cut. So we can film it and show you how easily the liner wanders around the 45-degree bend. And then, of course, later on, now you have the pre-folded liner in the pipe and you want to bring it back into its round shape. What we heard before, for example, from the U-liner, you can use steam or you can use hot water. All that is not necessary with an inserted hose, with a flexible hose, because you can only use air pressure. So that means what you do is you put pipe plugs on both sides. Once this liner is installed, you just blow air inside the liner, then your tapes will pop up and the liner goes from this U shape back into the round shape. So that means there is no process really happening on site, like for example with the other technologies in the market that could have an influence on the quality of the material. So now we have installed our liner, and the liner now sits loose fit in the existing pipeline. So now we have to connect it to the existing pipeline system. And this is why we need end fittings. Those end fittings can always be adapted to the needs of the client, of the pipeline owner. The end fittings come with a flange, so you can flange it onto a flange on the existing pipeline. If you don't have a flange, you can create a flange as well. You put a gibolt, a multi-joint on, you can weld a flange on if it's, for example, a steel pipe, and then you can connect this connector to it. I will not go now too much into detail how the connector technology works, as we are, of course, a bit limited in time. Let's just say in general, it is a clamping mechanism. You see that the different connector types, they basically consist of two main parts that clamp the connector, or sorry, that clamp the liner and hold the liner in place. And then the connectors are connected to the existing pipeline. If there is more interest, of course, if you want to learn more about the technology, how those connectors work, we can, of course, always discuss that separately. What's more important is that I would like to show you a bit what's out there, what has already been done with flexible liners out in the market, which type of pipelines have been renewed, and what you already can see. Basically, this technology has been used in over 50 countries in the world with a lot of private clients, like, for example, the American Navy, or also with a lot of public clients, like the city of Rio de Janeiro, or also the city of Phoenix over in the US, but that's of course just a few examples. Then let me show you the first project, the first pipeline here now that has been rehabilitated with a flexible hose. So that's an example from Sydney. Of course, I'm based in Australia, so yeah, there is a bunch of Australian examples now in my presentation, because it's always easier for me, of course, to speak about projects where I was directly involved, because I have the most knowledge. So this is a job that was done for Sydney Water, the water utility of Sydney in Australia. They are the largest water utility in Australia and New Zealand. And they had an existing pipeline. The pipeline was actually abandoned, and they wanted to bring the pipeline back to life. The pipeline, they performed pressure tests on the pipeline before. The pipe could not hold the pressures anymore, so that means the pipe would leak if they would put it back live. So they relined the pipe. The existing pipe went under a railway corridor here, what we see in the picture in the middle, and we had also 4 45-degree bends in the run of the pipe. The alternative solution for Sydney Water in this specific case was to install a new pipeline using HDD, so direct horizontal directional drilling. But with the circumstances and the area where the drilling and with the rail corridor and so on, you see the price in Australian dollars here. And you also see the price in Australian dollars for the installed premise liner. And yeah, I think you understand why the client in this case decided to reline the existing pipeline and not to install a new pipeline with another trenchless technology. What's also quite interesting is the speed of installation. So the entire pipeline could be rehabilitated in only one working day. So inserting the liner, inflating the liner, and installing the end fittings, only one working day. Fairly short lengths, but for 45-degree bends. The next project is in Brisbane, the capital of the state of Queensland here in Australia. And the urban utilities is the local water utility taking care of the greater Brisbane area, serves about 2 million people from memory. And this pipeline, like this project, was actually only finished about 5 weeks ago. So it's fairly newish, yeah. And the pipeline here runs on Ann Street. It's actually a BN 600 pipeline, cast iron cement lined. And Ann Street is one of the busiest streets in Brisbane. It's a 4-lane main road. And it's basically I would say it's the main connection road from the airport into the city center as well. So this is a road you don't want to shut down. And it is one of the main trunk mains, bringing water into the CBD, into the central business district of Brisbane. And the client decided to rehabilitate this pipeline with a flexible lining technology, because the pipeline also has several bends, and they also operated with pressures of up to about 11 bar. And it was a quite big job, but you can see also here on the numbers, 2.2 kilometers, but only installed in 5 sections. So that means what we see, for example, on the picture in the middle, the entire installation process could be done through very small access points, very small excavation pits. And I told you, it is a very important street in Brisbane, so you cannot just shut down the street during the day to repair a pipeline. That doesn't work. So what the client did here is they basically only created small access points to the existing pipe. They closed the pits during the day with steel plates, and then they came back at about 6:30 at night when the most of the traffic is gone, and then all the works were taking place at night. Then they again closed down the pits and came back on the next day. So also this is fantastic about such a trenchless technology, because you can stop after every installation step. It's not a continuous process. So you can, for example, insert the liner, come back on the next day. You can inflate the liner, come back on the next day. You can install one fitting, come back on the next day. So you can always keep the disruption to traffic, to locals, at a minimum. The next job I would like to show you is from Norway, and it's not about how specific the project is or how long the installation length is. No, it's not about that. It's about the picture on the left-hand side, because I want to show you the size, the footprint of such a rehabilitation job. You see here that, well, that's maybe a Norwegian thing. They actually have at some specific points maintenance chambers as access to their potable water pipelines. And we used such a maintenance chamber as access point to rehabilitate over 150 meters of water pipeline. So you see, no digging at this specific point was required. Your flexible hose can be inserted through basically a 90-degree bend through the maintenance chamber, because it's a flexible hose, so you can just bend it down and bend it into the existing pipeline. So it reduces definitely the impact on the environment. And we speak more about that on the next project. That's a job from Spain, rehabilitation of about 10 kilometers of asbestos cement pipeline. So it was also a trunk main in this case. And the main issue that the client, the water utility, had here was that the pipeline runs through numerous private properties and to basically enter physically private properties, to dig up the ground, and then to install a new pipeline. To get the permits for all of that takes forever. It would have taken years and years. But if you only reline the existing pipeline, you don't physically enter the property of someone, so you don't need a permit for that. So by working with a trenchless technology, in this case with an inserted hose, the amount of permits could be brought down from about 600 to only 25. So that means the job could be done right away. And then let's have a look maybe on the charts on the left, because that's extremely interesting. So in general, the rehabilitation of the project versus building it new brought down the price by over 30%. And we already spoke about the land permits, of course. The next thing is the installation time. So the estimated installation time for the new pipeline was about a year, and the rehabilitation of the entire pipeline with an inserted hose could be done in only 3 months. So we reduced that by 75%. Then, of course, the green footprint becomes more and more important. And for this specific job, for example, we performed some calculations, and actually the CO2 reduction that could be achieved by the limited amount, the limited use of machineries, for example, limited amount of trucks that were driving back and forward, was over 95%. And that also reflects a bit also in the last number, which is, of course, the Earth movement. The Earth movement could be reduced by nearly 99% because, of course, we only had a small access points to access the pipeline, and it was not necessary to dig up 10 kilometers of pipe. I mentioned before that with inserted hoses, you can also rehabilitate very, very long shots, long pipelines. This is a project that has been done in Germany, and it is a pipeline that is laid under the Baltic Sea in an estuary in northern part of Germany. And this pipeline needed rehabilitation. So in this case, a liner was inserted over the length of over 1.2 kilometers from access point to access point. And also what you see on the left-hand side on the picture, that's also the beauty of such a technology. You can, the entire pipeline, so 1.2 kilometer of new pipe comes on only one truck, only one transport reel, and you basically only need 4 people to install it. I have a last project for you that I would like to share with you. It is quite a special application. Again, it's a job here in Australia, a job that has been done about a year ago in Newcastle, which is north of Sydney. And the pipeline owner, in this case, Hunter Water, had a failing DN900 pipeline. So the pipeline was leaking, and we see on the right-hand side the run of the pipeline. So the pipeline has 2 opposing bends of about 22.5 degrees. It runs under a main street that leads into an industrial area, and then it also runs under a highway access road. So in general, not a road you want to shut down. And Hunter Water, in this case, was looking for the rehabilitation of this DN900 pipeline. We spoke before that the largest flexible hose available in the market, in this case, the Primus liner goes up to 500. So there is no DN900 liner available in this case. So the client decided to install a combination of liners. And we also spoke before, it is a self-supporting liner system. So it can sit by itself, like stand alone in the existing main. So in this case here, the customer then decided to install a combination of 3 450 liners, because this could give him the best flow. So if you would, for example, install only one single DN500 liner, the flow would be reduced to about 25%. And that's, of course, nothing you want. And with the installation of 450 liners, so that's the best fit that you could get in this case, the flow could be reduced to only about 60%. And with the small friction coefficient that we discussed before, and then only with the short lengths of about 160 meters, the engineers of Hunter Watt in this case gave it a check, and the installation could go ahead. Yeah, that's it from my side, everybody. I hope it was informative for you, and I'm also looking forward to your questions.
Thank you very much, Heiko. That was really informative. I mean, I know nothing about pipelining, and I found it very interesting indeed. We do have a question. Oh, we have several questions. Are you using any technique to confirm that the main has been inflated 100% along the section?
We don't use a special technique for that. This is all tested before. So we use a specific tape to tape the liner into its shape. And then all the bursting has been tested. So what we do here is that we control the amount of air that not the amount of air, but we control the air pressure that we have inside the pre-folded liner. And we know that we want to bring this air pressure up to 1 bar, because we know that at 1 bar, the 5 layers of tape that hold the liner together will open up.
Okay, but you don't use any cameras or nothing like that you can put down the main to ensure that you have full expansions, therefore you don't have a flow reduction, that's all?
No, we don't do that because it is not necessary. You could basically, after the liner is in the existing pipeline, you could drive into straight sections with a CCTV camera. That is possible, sure. But due to the fact that the liner is black from the inside, you would actually only see black. So it wouldn't tell you much.
Okay. Another question we've had. All the pipelines you've shown are just on straight lengths of main. What happens when you have connections? How is it you do a connection, a house connection, a property connection into that existing pipeline? And one of the experiences I've had before on the leakage side is that when it wasn't sealed properly, you had water ingress going between the existing pipe and the new lining pipe, which caused a pressure drop and the like. So how do you do that?
Yes, absolutely. So what you cannot do, and this is something you can do with other technologies, but then you of course have the issues that you just described. You cannot drill a hole into the liner once it's inserted into your existing pipeline to, for example, establish a house connection. So that means that every rehabilitated section with premise line has to end, or also with any other inserted hose, has to end with a proper end fitting. And onto that end fitting, which comes in a flange, you can then connect a T-piece, or you can connect a valve, but you could not drill directly into the inserted liner. So that means well, it probably depends always a bit on the specific country. Here in Australia, for example, we don't use this lining technology a lot for reticulation mains, exactly for the fact that you cannot just drill into the main. In the city of Moscow, for example, our company, for example, has very good experiences. So they do every year kilometers and kilometers of retic mains right in the city with flexible liners, but they still have to dig down always where they have a connection.
Okay, we have another question. Is your liner DWI or RAS approved?
So the liner, help me out, DWI was?
Drinking Water Inspectorate, which will be a UK-based thing.
Yeah, sure.
Is generally into the US.
Yeah, right. Yeah. So we do hold the potable water certification over in the US, also in numerous countries in on Europe mainland, I have to say, also here in Australia, for example. With the DWI approval, I would have to go back to my colleague over in the UK if we meanwhile hold that or not, because I am, to be honest, not sure about that at the moment.
Okay, another question. What is the life expectancy of this? So are you putting on once you go inside the pipe? What is it we're looking for? Is it comparative to traditional 40-50 years of pipelines or what?
Okay, so it is not just a temporary fix. So it is definitely, you have to consider it like a new pipeline in an old pipeline, and all the design on this pipeline, I did not touch on that now, but the liner is actually designed to a lifetime of minimum 50 years if you operate the product 24/7, 365 for the next 50 years at its maximum capacity, which you will never do. So this liner, for example, here that I hold in hands is rated to 25 bar operating pressure. If you insert it into your 150 main that is rated to maybe 10 bar, you will never ever basically give full stress to this lining material, which then of course has an impact on the life expectancy of the liner. So 50 years minimum, but under real operating conditions, unless we're talking like industrial applications where you always are on a maximum capacity, the life expectancy is more towards 100 years.
Okay, now we've got one now, which I'm fairly positive you won't answer. Any general comparison with other trenchless techniques in terms of price? Where do you sit compared to the other ones?
Yeah. If I compare, for example, our material to, let's say, slip lining, what we have seen before, I would say that the material itself is more expensive. But you cannot only compare the materials, because if you will compare such a liner to a steel pipe, it's more expensive. But with a steel pipe, you have to dig up the entire road, you have to do this, you have to do that. All the installation processes take way longer. And especially in a country with high labor costs, like for example, here in Australia, you want to keep the installation times at a minimum. So that means, for example, that you can, and it's jobs that we have already done, also here in Australia, you can rehabilitate 500 meters of pipeline. You can install the liner plus 2 fittings, 500 meters in only 1 working day. And according to my knowledge, there is no other technology out in the market that can do that.
Okay. Another question's come in. Based upon your slide you've shown where you're 30% cheaper than traditional pipelines. Obviously, you have a mobilization charge where you have to mobilize into the country, specifically, just say into the US. Does that include mobilization fees, or is that just on-site fees?
So what happens here is that the liners, and not only our liner, also other flexible liners, are being produced in country X, in this case in Germany, and then the materials are being transported in containers to the specific country. And then, for example, in the US or in Australia, doesn't matter, in China, in the UK, the same thing. You have then certified installation partners that perform the installation for you, so you don't have to move your teams from, for example, Germany to the US to perform the installation. You only move the materials. And if I transport, for example, let's say 1 kilometer DN 500 liner here to Australia, that costs me in a 40-foot container not even 10,000 euro. So if I look at an entire cost of an installation, that's 0 point something% of the entire project.
Okay, thanks for that. Can this technique also be used on wastewater pipes? And if so, what experience do you have that you can explain?
Yeah, the technology can be used on wastewater pipelines, but they have to be pressure pipelines. So if it is sewer rising mains, sewer force mains, sewer pressure mains, yes, this technology cannot be used on gravity mains because it is and will always remain a flexible liner. So it needs the operating pressure of the main to keep its round shape. But with sewer rising mains, for example, yes, the company Primusline, for example, has very good experiences. And we have installed numerous sewer rising mains, for example, in the UK, in the US, in Germany, and also here in Australia.
Okay, that's excellent. We are out of questions now, unless anybody wants to drop another question in to the chat box. I don't think we have. Do you have anything else to say before we finish?
Well, what I want to say is that people here, for example, in Australia, they're open-minded to new technologies. And it's not only about our specific system, it's about trenchless technologies in general. There is so many good stuff out there, and it would be fantastic if the mindset of the people would be open to modern technologies, because they can save money, they can save time, and they can prolong the life of your asset. Thank you.
Yeah, I know. Just got one more question coming from Sarah. It says, what minimal internal pressure can the liner stand during surge events? I'm not sure whether you mean minimal or maximum during surge.
Yeah, probably. So if we talk about surge pressure, so every liner is actually I mentioned before, every liner is rated to a specific operating pressure. So let's just think about the DN200 Kevlar liner, for example. This one is rated to an operating pressure of 40 bar, 40. If we then think about the burst pressure of the liner, so all the operating pressures are actually calculated on the burst pressure of the lining material. And then there is a safety factor and a lifetime factor that is calculated, and all of that. And then that brings us to the maximum allowable operating pressure for a DN200 aramid liner, for example, 40 bar. So that means if you install this 40 bar liner into your existing pipeline, you can have surge pressures of 10, 20, 50, even 100% on top. And the liner itself would not burst. Probably everything around would burst and all your valves would burst. But the liner itself, specifically Primusline, has actually been designed for the rehabilitation of high pressure gas pipelines. And the same liner structure, only with a TPU inner coating, is still used for the rehabilitation of gas pipes and also of diesel and crude oil pipes, where of course the safety factors and so on are way, way higher. But that should just show you that basically all Primus liners you install can easily accommodate surges because it's in their design.
Yeah, she's come back. It's definitely talking about minimal pressure. She's talking about negative pressure. So I suppose,
sorry.
Yeah.
Okay, right.
It's definitely negative pressure.
Yes, okay. That's a different story. Okay, so with negative pressure, like I mentioned before, it is a flexible lining technology, and it will always remain a flexible lining technology. So if you have a negative pressure scenario in your pipeline, what will happen is that the liner will collapse. Absolutely. Yes, that happens. But it is different to, for example, CFPP liners. With the CFPP liners, what I've, for example, seen is that if you have certain negative pressures, that the liners might just be ripped off the wall, and then, of course, the liner is destroyed. This liner here is tested for negative pressure. And like I just said, what happens at negative pressure is that the liner will collapse. And when the pressure comes back, the liner will open up again. We do have specific tests for that, where we, for example, we took a specimen, we went into minus 0.6 bar, we kept it for 10 minutes of time, we went back to an operating pressure of 10 bar, we repeated that in several cycles, and we did a burst pressure test on the virgin liner, and then after the test, we did also a burst pressure test on the tested liner, and the results showed that the vacuum did not have any influence on the lining material.
Okay, that's excellent. We had a question. What is the role of water quality? I suppose. I mean, what is the capability of the pipeline maintaining a good water quality as you would do in a traditional MDPE steel main? Does it affect it at all, or do you lose any chemical leaching through the pipe wall or nothing like that?
So no, you don't. Absolutely not. After the installation of the liner, there's of course a disinfection process, the same that would be if you installed an HDPE pipeline, for example, or a new HDPE pipeline, slip lining, etc. So there is a disinfection process, and there is no. It's not that like the plastics would just swim away over time. So we have been installing this system now for nearly 20 years. And the water quality of a pipeline that is rehabilitated with such a flexible liner is the same water quality that you have also in, for example, a HDPE pipeline.
Okay, then that's fantastic. We are about ready now to wrap up. We're about on time. A couple of people have asked if they can have a PDF presentation. You see Heiko's email address on the bottom of the screen. If you can contact him direct, he will share with you what he can share. As always, this video will be loaded to the Water Loss Specialist Group's webpage on YouTube, so you can get into the video again at any later date. So with that, I do thank Heiko for a fantastic presentation, really informative. I've learned a lot, and I hope everybody else has. So with that, I thank you for your questions, and I thank everybody for attending. So thank you, and speak later. Bye-bye.
Thank you, everybody.